So our next speaker is Dr. Jim Lyke. And so Jim is a technical advisor to the Space Electronics Branch of the Air Force Research Laboratory at Kirtland Air Force Base in New Mexico. He's an AFRL Fellow and an adjunct faculty member at the University of New Mexico. He has a PhD in electrical engineering and has specialized in the study of advanced microelectronic architectures and packaging technologies, with over 100 publications and 11 US patents. So today he's going to talk to us about reconfigurable electronics and advanced packaging. Okay.
Okay, thank you. Okay, good morning, everyone. Really looking forward to spending the week here at Caltech to study these problems. And of course, I'm going to bring a different perspective. I look at this as a challenge of bringing together a number of future trends, and I'll talk about some of them and disruptive technologies and the role for all of that. It's changed the way that we use electronics in our life. How we might apply these ideas to what I've been calling extremophile spacecraft problems. So we're talking about making electronics that work on the surface of Venus or on Titan. And we had one experience, and this was in the 90s, of trying to create specialized electronics to work on a problem involving probes that would work with extremely high G-forces on the south polar region of Mars, where we had to make electronics that worked down to minus 130 degrees. And we thought that was a hard problem, but compared to some of the things that you're talking about here, I mean, this is a cakewalk. So I'm glad that we have 15 more years of technology and thoughts about how we might solve these problems. But I want to talk about first just disruptive technology. It's known that ideas like even Moore's law were originally disruptive, have become sort of an expectation. But there's this idea that there's the sustaining technology where there's a steady metered improvement. And then there's the disruptive technology, which progresses at a much faster pace. The thing to notice is a couple of things. One is that the disruptive technologies start out being very ignorable. Their performance is far below the norm. So they might be clunky technologies. Things like field programmable gate arrays and personal computers are examples of those, where the very first personal computers were hobbyist machines. They were toys, and they weren't really in the realm of anything serious that you would use. But eventually, you see the slope. While in the case of the PC, the mainframes continued to get better, and you could always count on them improving somewhat every year. The personal computer, which was being ignored, eventually got much, much better, to the point where when you're out here at some point, you have this sort of clash where the new technology surprises. It's disrupting the status quo. And so that's an important idea. And I think a few things. I mean, if we see it coming, it's not disruptive because we could have predicted it. So that's an important characteristic. And a lot of the disruptive trends were actually understood by the companies. They actually had fledgling investments in disruption, but they ignored the consequences of those. But then there's also the aspect that we work on a lot of different strange technologies and scary technologies, and not everything is necessarily disruptive. Just because it's different doesn't mean. So we can't. That's another reason we can't. It can't just be a new technology for its own sake will be disruptive. Some things never see the light of day. So Moore's law. I mean, it's a very predictable trend. We know what to expect. I guess lately we're starting to worry that we can't count on Moore's law. And then there are the things that come out from nowhere. And those are the disruptive technologies. And I think we have to address those. what became of Moore's Law? I mean, Moore's Law is still here, but it was hard to look at the original integrated circuit and say, well, this is the beginning of a revolution. This is what Kilby did in the 50s. When Robert Noyce in about 1961 began to create the first planar integrated circuit, we began to see something that looked a little, at least more familiar as the beginning of this revolution. But Moore himself didn't coin the idea of Moore's Law. He didn't ever, I don't think he called it Moore's Law in about 1965, it was about 4 years after this. So Moore's Law was the disruptive idea. It was one of the key disruptive ideas. And you can, with Moore's Law, you can count on the idea that you can double the number of transistors every 18 to 24 months. And it was the driver of other disruptive technologies like the PC. That rapid slope was largely due to the Moore's Law advancements. The work at Palo Alto Research Center that laid the foundations of modern computing ideas. They took advantage of the knowledge of the future. And some people are saying it's starting to end. I mean, we're already seeing at the sort of the 20-something nanometer node, lots of difficulties. We're not solving the challenges in extreme UV lithography. We're not seeing necessarily the power improvements that we had hoped for. And some people are starting to say, hey, Moore's Law is over. However, I think we easily can get 6 more orders of magnitude through trends like 3D packaging and through work that eventually someday, I mean, we keep talking about ideas like molecular electronics, and I think in some sense my own experiences with these technologies led me to conclude some things that I hope will be useful in the workshop. We've had our own work with thinning electronics, and I fortunately have had the opportunity to work with people like Glenn Foreman, who's here from General Electric, on a problem of thinning electronics below the thickness of a piece of paper, which is about 100 microns thick, to create foil-like flexible electronics. And then you realize if you can do that, you can maybe start to stack these like plies in a multi-laminate system. And that furthermore, through breakthroughs like the through-silicon vias, where we can put tiny copper or tungsten plugs by the millions per square centimeter in an integrated circuit, that we can have not just 3D stacks of these thin plies, but within them, the chips themselves are stacked anywhere from 2 to 20, 30 layers. So now we can begin to believe that maybe we have a chance of extending the ideas of Moore's Law for another several generations. And so I think that's an exciting idea. Molecular electronics is the other idea. It's like, well, once lithography fails, once other things start breaking down in the traditional semiconductor roadmaps, what are the new trends? And so with molecular electronics, which I don't have time to really go into a lot, I think we're looking at new trends like self-assembly, defect tolerance, the ability to self-organize very complex systems, 10 to the 18th, 10 to the 20th primitive elements. And so the reflections on this had led me to look at the idea of how to make very, very primitive blocks that by themselves are very simple, but in extremely large ensembles can form very powerful systems. And I think that when you start to look at what I call extremophile problems, you begin to look at, well, what can I have that works at 500 degrees C? What can I have that works off of almost no energy, and you begin to say, well, I think I can look at some very simple things. Well, maybe there is more intersections here between molecular electronics or trying to make very simple systems that scale and the extremophile spacecraft problems. So I won't dwell on this slide, but I mean, we were beginning to look at some very radical concepts for forming molecular electronics on the capsids of plant viruses. And in doing that, trying to create a system that we could make into a scalable fabric that we could layer onto a silicon chip and create essentially a new kind of supercomputer. And this is work that actually is over a decade old now. But the architectural underpinnings, we were looking at the idea of very primitive blocks that could self-organize, self-assemble, and form computation fabrics. So when I look at the energy projection ideas that Adrian was just covering, I thought, well, we need a type of new smart fabric so that I can cast multifunctional structures into sheet form where many cells are involved and the cells are reconfigurable and they self-organize. So we need architecture underpinnings of how to do that and then look at what we can physically build and see if we can yield something from all of that. I'm also excited about trends in additive manufacturing, and we do have experts from the University of Texas, El Paso, probably one of the world's leading centers in the frontiers of additive manufacturing research. So we can move from things like the maker bots, which some of us have in our garages, to more creative exploitation and eventually being able to do multi-material and having additive manufacturing not as the only thing, but a tool in a large toolbox of techniques and technologies. And I've left this material in my presentation. I won't be dwelling on it because I have a lot of ground to cover, but you could probably look at this a little bit more in leisure, and I know that these proceedings will be made available. But we began to look at the ideas of what could we do with in situ 3D manufacturing, where we actually take measurements of things as we're building them and then adjust the computer-aided design. So I could take an S parameter measurement of a microwave circuit and then adjust the filter that I'm about to build to take into account the variations of the thing that I just put in the system. So this idea of dynamic manufacturing is also an exciting idea. The idea of print and pick and place, where I take pre-built modules and integrate them together to form a system. Okay, so in my title slide, I did caveat this was eclectic. I'm jumping from topic to topic. So I've talked a lot about packaging, talked just a little bit about 3D manufacturing. Now I want to talk about reconfigurable systems, and I think this is an agent for disruption, an agent for change. I think of reconfigurable systems as a way to embrace change in a very specific way. It's like a software-definable system. So field programmable gate arrays, we're hearing about software-defined radios, software-defined networks, software-defined everything. And that's kind of, I think, intimating of much bigger things that can happen in the future with reconfigurability. So in engineering reconfigurable systems, we're trying to develop knobs that we can turn from a distance. So think interplanetary. I can actually reconfigure systems and fabrics from great distances. And I think as we advance, as we find things like the field programmable gate array, which has dramatically improved through Moore's law over 20 years to become essentially a fabric that's in almost every type of electronic system. We'll see other things in future breakthroughs. There are three benefits for reconfigurability. So I feel strongly enough about this that I've tried to work out the taxonomies and ideas about reconfigurability. But the first of these is just the idea that I can change systems from afar. So with a field programmable gate array, for example, it's like having a silicon chip whose function, like a blank CD, is initially uncommitted, and then I can change that. So I could actually reprogram the FPGA of a system on another planet from Earth and convey that functionality. That's the first benefit. I can fix design problems, I can adapt. The next is resilience and robustness, the fact that I can reconfigure around defects and faults. And then a benefit called X on demand, which I built a whole program around called plug and play, where we looked at time, the time it takes to build systems and accelerate that time. So in a problem of plug and play, and I'm just going to jump through this material really quickly. We were focused on how to build systems much faster. There had been, and really still today, is this problem where we try to build systems and they take forever. They're multi-billion dollars. We have schedule slips of years. And we were trying to figure out how to build a spacecraft in a week. And so in doing that, we were trying to take a system with many moving parts, and the parts are built in different places, and bring them all together very quickly to form a system. We know that some of the causes of delays in large systems is due to this kind of problem we call the marching army, and when you have a schedule slip, this whole army is a standing army. So we began to look at reconfigurability to conquer problems in time and complexity. So we thought of our pursuit as a fight against the growing complexity of future systems. We still have that problem. We did not solve it. We brought some ideas to bear. And so what we were trying to do is to figure out how to create a spacecraft in less than a week. Now, how can I do that? Well, I've talked about the field programmable gate array already in this talk, and I think it represents an interesting counterpoint. If you don't use an FPGA, you have to build the silicon from scratch. That fabrication takes a certain amount of time. Let's say it's 6 months. If I have an FPGA, I don't have to do that. So I can automatically short circuit the time. There wasn't anything magic in that. The fact is that I did build the FPGA, but I built it in the past. And so the idea of binding functions to things after the fact, that's another key idea with reconfigurability. So we can use it to beat time delay. So we could look at a spacecraft as a hierarchical assembly of these reconfigurable parts. So whether we're talking about a spacecraft orbiting the Earth or some interplanetary system, we can look at this as not just a building block system, but each of the building blocks can be adapted, can be altered under different conditions. So these are some of the principles. We worked out a system called SPA, Space Plug and Play Avionics, and just, again, in the quickest way I can try to explain it, we were trying to bring the benefits of a personal computer to a spacecraft. Where a computer has mice and keyboards, we have reaction wheels, gyros, power systems, and we were trying to bring this Lego-like fluidity of putting systems together. I still feel that this is a very important pursuit, and I just want to mention it because I think it is something, as we look at creating a toolbox for doing these interplanetary systems, we want to have this type of thinking. It was something on one slide I can try to convey. We have a bunch of components that are self-describing, and so this self-description and networking allows us to put very large systems together with many hundreds or thousands of modules. We have a software framework where that self-description is used to facilitate the connection of the pieces of the system. So a thermometer announces itself as a thermometer. An application that uses thermometer information finds the thermometer. And so this is really the heart of any plug-and-play idea. And so the idea of creating these composable systems. So what I'm talking about here is one very applied form of reconfigurability where I took one of the three benefits and I've built a whole architecture around that. And so we can do those sorts of things. So then I would make as eventual suit the idea of a programmable matter, because that to me is plug and play in the extreme sense, is moving to essentially infinitesimal blocks that can be bound together under program control, that can be bound with functions under program control. And so if we're trying to build a scalable fabric, such as an energy projecting system, we might envision many simple cells that can be formed together to create a fabric that we can do something with. I believe that the first computers, the ideas of the von Neumann computers were the beginning, but in a century maybe from the inception of the von Neumann computer, we will have in the future fully reprogrammable systems that may in some sense give us glimpses of what will eventually be a programmable matter system. So I hope this doesn't sound too scary. I think it's actually very doable. We may not get to actually programmable molecules, but we'll get to programmable small blocks. It's already beginning to happen. And so maybe that's the ultimate quest. This Venn diagram is sort of a taxonomy of the reconfigurable system, starting from the von Neumann computer, going to the FPGA, in which any digital system practically imaginable can now be formed as a software-defined piece of intellectual property. Over time, we will master the ability to make reconfigurable analog systems, reconfigurable wiring, and we're already looking at ideas like metamaterials, plasmonics, and configurable mechanisms. And so eventually we'll be able to build entire systems under the idea of reconfigurable software control. Going back to the ideas in molecular electronics, I mean, we were fascinated to look at very simple viruses where a number of very primitive building blocks of protein spontaneously self-organized to form the structure of a virus, and we began to wonder, can we do this with spacecraft? Could we do this with, say, your energy projecting system ideas, where these form the tiles that allow us to self-organize? So to me, the virus, the reconfigurable cell, and this are really just differences in degree and interpretation. That and in fact, we can do these kinds of things. I'm convinced that we have the technologies to do this. We can begin to interpret the plug-and-play systems that we were building in our own laboratory as large reference architectures that gave us insight into what we might eventually take into another direction. So maybe we need a new kind of Moore's law. But in adaptive wiring, which is one of the applications of these reconfigurable cellular designs, we can create a system whose wiring patterns can be controlled under software. We can form 2 cells, more than 2 cells, thousands of cells, and each of the local patterns can be configured on demand. And we can make this adaptive, we can make this self-healing. We can also inject measurement into the system. We can temporarily form a software path that connects a wire so I can measure voltages. We can make a system that is fault tolerant. If the wire breaks, we can form a new connection. And so we had done some work to look at building very simple demonstrations we had done a 48 tile cell array. And all this was reconfigurable wiring. And so we've implemented these kinds of ideas. We can look at software radio systems in the same way. We can use adaptive wiring and antenna arrays to put together software radios on demand. There's a lot of work in, obviously, cognitive radio, and certainly at this point it's nothing new. So one of the things we did in plug-and-play and reconfigurable research, we began to look at the idea of what is the reference architecture for a smart cell? And we began to look at the idea that we have payloads and configurable elements that we put together to form a scaled system. And so maybe we can begin to create the tiles of a configurable fabric, and we look at the extreme environments and say, well, what of these reference architectures do I have to take away to operate on Venus? Which ones do I have to add to work on the surface maybe of Titan or other planets? And it could be that we create this reference architecture that works at room temperature, and then we study how to adapt this and create the tools and infrastructure, because there is a lot under the hood that I'm not talking about. And even ideas like CubeSats, we could apply this idea to where we have essentially very Lego-like CubeSats. We can create ideas like pixelated antennas, where I image the antenna pattern, and if I set a 0, it's a dielectric, and I set it as a 1, it's a conductor, and I pixelate that idea. So we can start to come up with a lot of schemes, and we've been working with the Air Force Office of Scientific Research to study the possibility of making these very small, this is a millimeter scale cell, which might have tiny bits of computing and communications inside. And then someday going all the way to the small, essentially virus that we form a circuit around. There are a lot of key ideas, and just briefly, I'm going to just introduce or just touch on, almost identify the elements of these future reconfigurable cellular systems. And there's many different cell types. We can talk about configurable wiring, configurable thermal storage, configurable energy storage, programmable mechanical attachment, cells that route light, fluid, whatever. I mean, I think we can talk about a variety of these. And so we need to have the idea of what is a cell. And a cell there's an atomic notion of a cell that can't be subdivided. So when I have the black box, if I break the black box, all bets are off. So we have this idea of a modular structure that comprises the building blocks. And then we can do things like guided self-assembly. So now we can think about storing a bunch of tiles and have them somehow organize themselves to form something useful like a dish array or some structure that might be building blocks for a spacecraft. And we can use the configuration management ideas that we have in things like FPGAs to essentially provide the DNA that drives this self-assembly. And so we can form non-trivial collectives. If we have that ability, we also have the knowledge to repair the system so that we can restore it to its normal configuration. We can also do concepts of self-reproduction where the DNA we break off or bud, the assembling, we can generate more copies of the same structure. In doing this, I believe one of the greatest struggles we have is computer-aided design and tools. And we're used to using very powerful descriptive languages, that's what we call them, to specify computer programs like C and Java and MATLAB. And for digital systems, over time, we began to learn that schematic capture was too slow for us to express millions of gates of computing. So we began to create languages like Verilog and VHDL. So similarly, we have to create the languages for reconfigurable smart systems in the future. So if I have all these smart building blocks, I essentially have a piece of intellectual property. It's like a program script that I feed into the system, and I can begin to tell it what it needs to do. So that's a very exciting idea. The notion of the advent of a Megacompiler, and where I have a push-button tool flow that allows me to convey the idea of what the wiring is, what the communications protocols are, and what the mission is going to be done with this block of cells, express it in a high-level language. So I've covered a lot of ground very quickly, and I think the notion was that over the period of this week and in the study that we're conducting, that we can study these ideas to the degree that they have application. I believe that the future is about reconfigurability. I believe that cellular architectures make a lot of sense, and I think that we can apply them effectively as a sort of meme or an idea for doing these scalable fabrics for interplanetary applications. These will give us properties that are very desirable, robust. We can optimize for power. We can make blocks that look simple yet scale to form very sophisticated systems and use powerful ideas from plug and play like self-organization. This stuff doesn't happen on its own. You have to create a lot of great tools behind it, and I'm already giving you some warning about the problems that are solved by having synthesis tools that, for example, like compilers that translate ideas into primitive elements. So someday I'll be able to have a language that actually can be conveyed into a bunch of very primitive elements that will do arbitrarily complex things. And so I think that in this case, the application is to create the fabrics for extremophile spacecraft. So kind of in closing, I've talked about the idea of disruption and its role. We have to think disruptively. These are extremely challenging problems, and they're not going to be solved in simple incremental ways. They're going to require a number of breakthroughs, and we can't schedule breakthroughs. I mean, sometimes we don't know where they come from. That's the nature of disruption. I think that reconfigurability and cellularity are key principles, and I think that the ideas of plug and play that are so mundanely represented in an idea like a personal computer can be applied much more profoundly to create these future systems. And so I look forward to being able to work collegially over this week to discuss these ideas. And thank you for your time.